Welcome to day 11 of our 15-day beginner data science sprint. In the previous lesson, we understood the basic machine learning workflow. We learned about features, targets, training data, testing data, baseline models, and data leakage. Today, we are going to put those concepts into practice by training our first machine learning model. Our goal is simple. Can we estimate a student's final score using information such as study hours, attendance, previous score, sleep, and classroom participation? By the end of this lesson, you will be able to train a linear regression model, generate predictions for unseen students, compare the model with a simple baseline, and interpret MAE, RMSE, and R squared in beginner-friendly language. Most importantly, we will not treat the model as magic. We will understand what its output mean, what they do not mean, and how to judge whether its predictions are useful. Before writing any code, let us understand the problem. Machine learning problems can produce different types of outputs. For example, we want to predict a category. For example, will a student pass or fail? Will an email be spam or not spam? Will a customer leave or stay? These are classification problems. But today, we want to predict a number. The final score may be 52, 71, 84.5, or some other numerical value. When the output we want to predict is numerical, the problem is called a regression problem. So remember this simple definition. Regression predicts a number. Our target today is final score. The remaining columns such as study hours and previous score will be used as features. Features are the inputs given to the model. The target is the value we want to predict. Let us first look at the final result we are working towards. By the end of the lesson, we will have actual scores and predicted scores like this. Let me share the screen. So this is how the scores will look like. The predictions will probably not be exactly equal to the actual scores. That is normal. The difference between the actual value and the predicted value is called the prediction error. Our job is not to create a model that magically predicts every value perfectly. Our job is to create a model that magically predicts uh, that performs reasonably well on students it has not seen before. So our job is not to create a model that magically predicts every value perfectly. Our job is to create a model that performs reasonably well on students it has not seen before. Let us begin by tools required for today's lesson. But before that, I want to summarize the definition that we have discussed. So first was regression. So regression predicts a number. That is the first important thing. Then the features are the input given to the model. The target is the value we want the model to predict. The difference between the actual value and the predicted value is called the prediction error. And this is one example of actual score and predicted score. Now let us create a new code cell and write run the cell. Pandas will help us work with the dataset. NumPy will help with numerical calculations. Matplotlib will help us visualize the model's prediction. Now import the machine learning tools. So let's import one by one. From sklearn.model selection, we import train test split. From sklearn.linear model, we import linear regression. From sklearn.metrics, we import mean absolute error, mean squared error, and R2 score. From sklearn.dummy, we import dummy regressor. Let us understand these imports. Train test split divides the dataset into training and testing sections. Linear regression is the machine learning model that we will train. The three metric functions will help us measure prediction quality. Dummy regression will create a simple baseline model. A baseline is an intentionally simple approach that gives our machine learning model something to beat. Now let us load the clean student performance dataset. So let us use the previous dataset. Now what should we do immediately after loading a dataset? We should inspect it. Never begin modeling without understanding the table first. So run display df.head. The first 5 rows appears. We may have columns such as student ID, study hours, attendance, previous score, sleep hours, participation, final score. Let us also check the shape. The shape tells us the number of rows and columns. Each row represents one student. Each column represents one variable or characteristic. Now inspect the column names. This step is important because the model cannot work correctly when we accidentally use the wrong column name. Before training the model, let us perform a few basic checks. So df.info. Look at the data types. The features we want to use should normally be numerical. Now check for missing values. So we did not expect any missing values in the dataset, and that is correct because we had already cleaned the dataset. The output shows us zero missing values in every column. This tells us that selected columns are complete. However, it does not prove that every value is correct. For example, an attendance value of 500 may not be missing, but it would still be unrealistic. So missing value checks are useful, but they are not the complete data quality process. Let us also look at the statistical summary. Observe the minimum, maximum, mean, and spread of each numerical column. Check whether the values appear reasonable. This connects directly to the data science workflow. Machine learning comes after data collection, cleaning, exploration, and validation. A model trained on incorrect data will learn incorrect patterns. Now we need to decide which columns the model will use first. Not first, but which columns it will use. We will use the following features. Now create X, capital X. In machine learning, uppercase X commonly represents the feature table. Each row contains the information available about one student. Now create Y, lowercase y. Lowercase y represents the target. This is the number the model will attempt to predict. Let us inspect both objects. Notice that capital X contains multiple input columns, but Y contains only the final score. The model will try to learn a relationship between these inputs and the output. Before continuing, let us perform an important check. Did we accidentally input final score inside X? No. That would be data leakage. The model must not receive the answer as an input. Imagine asking a student to predict the final scores while secretly giving them the final score. The result may appear perfect, but the model would not have learned anything useful. We should also be careful with features that may only become available after the final score has already been decided. For today's demonstration, we assume that all selected features are available before predicting the final result. We will now divide the data into training data and testing data. Right? Before xtrain comma xtest comma ytrain comma ytest equals train test split x comma y comma test size equal to 0.2, random state equal to 42, or any other number. Before running the cell, let us predict what will happen. If test size is set to 0.2, what percentage of the data will be used for testing? 20%. The remaining 80% will be used for training. Run the cell. Now check the sizes. The training feature rows and training target rows should match. The testing feature rows and testing target rows should also match. The model will learn from xtrain and ytrain. It will then generate predictions for xtest. Finally, we will compare those predictions with ytest. Why do we need testing data? Because checking the model only on its training examples would be like giving students an examination containing the exact question they already memorized. We want to know whether the model can work on unseen examples. The testing set gives us a more realistic estimate of performance. Random state equal to 42 makes the split reproducible. This means that when we rerun the notebook, we should receive the same training and testing rows. The number 42 is not mathematically special here. It is simply a fixed value used to make the experiment repeatable. Before training linear regression, let us create a simple prediction strategy. Suppose we ignore all student information. Instead, we predict the average training score for every student. This is not an intelligent model, but it gives us a baseline. Our regression model should perform better than this simple average based prediction. Create the baseline model. Train it using the training data. Now generate baseline predictions. Let us inspect the first 5 predictions. Before running the cell, predict what you expect. Will the values be different for every student? No, because the baseline prediction The baseline predicts the same training set average for every student. Run the cell. You should see the same value repeated. This baseline does not use study hours, attendance, previous score, or any other feature. It simply says, my best simple guess for every student is the average final score. Let us calculate its mean absolute error. Suppose the output is approximately 9. This would mean the baseline predictions are wrong by 9 score points on average. The exact result in your notebook may be different because it depends on the dataset. Do not focus only on whether the number appears small. We will need something meaningful to compare it with. That comparison will come from our linear regression model. Now let us introduce linear regression. Linear regression tries to model the target using a weighted combination of the input features. A simple version may look like this. So predicted final score equal to intercept plus study hour weight into study hours plus attendance weight into attendance plus previous score weight into previous score plus other feature contributions. The model learns the weight from the training data. A positive weight generally means that while holding the model's other outputs, other inputs constant, a higher feature value is associated with a higher prediction. A negative weight generally means that a higher feature value is associated with a lower prediction. But we must be careful. A coefficient does not automatically prove causation. The model identifies relationships in the available data. It does not prove that changing one feature will directly cause the final score to change by a specific amount. Student performance may also be influenced by motivation, teaching quality, health, family environment, examination difficulty, and many other factors that may not appear in our dataset. Create the model. At this point, model has not learned anything. It is an empty model object. Now train it. Before running this line, ask yourself, what information will the model use? It will use the feature values in X train and the correct final scores in Y train. Run the cell. Okay, because we had input this participation as a feature, and participation is not a numerical value. That's why it is giving an error. So what we can do is, before train test split, we can convert participation into a numerical value. So we missed this point. So let us correct ourselves. So I'll generate the code, convert participation to numerical value. So what it does is it updates the future columns to reflect the new one hot encoded columns, and then drops the previous one and inserts the new one. So let us run this. Actually, we don't want this. We want this to change. So I will select this and click on this button and run some code. What I want is value of 0.3 for low participation, 0.6 for medium, and 0.9 for high participation. I don't want 3 extra columns. I just want this. So I will accept it and let us run the code. So because we had changed our x earlier, so I think we need to run the code from starting again. So let us load the data frame, then see the head, then the shape, then the column, then the info, then we see the feature columns. Then we calculate the x and y and then display both x and y. Now we run this cell and now we have got the correct participation. Then we again split it, calculate baseline, fit the baseline, get the baseline predictions, get the baseline MAE, now model equal to linear regression, and finally fit the model. So you may not see any dramatic output, that is normal. The important change happened inside the model object. The model has now estimated its intercept and feature coefficients. Fit is the step where learning happens. Now let us use a trained model to predict scores for the testing set. So predictions equals model.predict x test. Before running this cell, predict the output format. Will we get one number or multiple numbers? We should receive one predicted final score for every row in x test. Run the cell. Now inspect the first 5 predictions. So you may see decimal values such as 55.78 for 2.21, 53.95, 39.73, 51.88. Final scores in the original data may be whole numbers, but regression models can naturally produce decimal predictions. We should not automatically round the prediction before calculating the matrix. Rounding removes information and can slightly change the measured error. Let us create a table that compares the actual and predicted scores. Now calculate the error. Calculate the absolute error as well. Now display the first 10 rows. Let us understand the columns. Actual score is the real final score. Predicted score is the model's estimate. Error is actual minus predicted. A positive error means the model predicted too low. A negative error means the model predicted too high. Absolute error ignores the direction and only measures the size of the mistake. For example, suppose actual score equal to 80 and predicted score equal to 74. The error is 80 minus 74 equal to 6. The model underestimated the score by 6 points. Now suppose actual score equal to 76 and predicted score equal to 70. Actual score equal to 70 and predicted score equal to 76. The error is 70 minus 76 equal to minus 6. The model overestimated the score by 6 points. In both cases, the absolute error is 6. Let us calculate the model's mean absolute error. MAE stands for mean absolute error. It tells us the average size of the model's mistakes. It uses the same unit as the target. Because our target is measured in score points, MAE is also measured in score points. Suppose the MAE is 3.59. A beginner-friendly interpretation would be, on average, the model's predicted final score differs from the actual score by about 4.2 points, or by about 3.59 points. This is a simple interpretation. This does not mean every prediction is wrong by exactly 3.6 points. Some predictions may be closer, some may be much farther away. MAE gives us the average absolute difference. Now compare it with the baseline. If the linear regression MAE is lower than the baseline MAE, the model is using the features to make better predictions than simply guessing the average score. That is an important first check. Now calculate RMSE. RMSE stands for root mean squared error. Like MAE, it measures prediction error in the same unit as the target. However, RMSE gives more importance to large mistakes. This happens because the errors are squared before they are averaged. Imagine two models. Model A makes several mistakes of 4 or 5 points. Model B usually performs well but makes one very large mistake of 25 points. RMSE will penalize model B more strongly for that large error. A simple interpretation is RMSE shows the typical prediction error while penalizing unusually large mistakes more heavily. If RMSE is much larger than MAE, the model may have some particularly large prediction errors. Let us investigate those rows later. Now calculate R squared. R squared compares the model with a simple mean based prediction. It tells us how much of the variation in the target is captured by the model. Its interpretation needs care. An R squared value closer to 1 usually indicates that the predictions follow the actual variation more closely. An R squared value near 0 means the model may not be performing much better than predicting the mean. A negative R squared can occur when the model performs worse than the mean based baseline on the testing data. Suppose the result is 0.81. A simple interpretation could be the model captures a substantial portion of the differences in final scores within this testing data. You may also hear someone say that the model explains 78% of the variation. That interpretation is commonly used, but we must not turn it into a casual claim. R squared does not prove that the selected features cause 78% of student performance. It describes how well the model fits the variation in this particular dataset and test split. It also does not tell us whether the model will perform equally well in another school, another year, or another student population. So this is a simple interpretation of R squared error. The model captures a substantial portion of the differences in final scores within this testing data. And this is a simple interpretation for RMSE error. Let us display the matrix clearly. The colon dot 2f formatting displays each value using two decimal places. Now pause the video and explain the most important output in one sentence without using technical jargon. A good answer could be, so this is the question. A good answer could be, the model's prediction is usually about 4 score points away the student's actual result. Your exact sentence will depend on your MAE. This is an important skill. A data scientist should be able to explain an output in everyday language. Let us create a visual comparison. Before running the cell, predict what each point will represent. Each point represents one student in the testing data. The horizontal position shows the student actual score. The vertical position shows the model's predicted score. Run the cell. A basic scatter plot helps us compare predictions, but it would be even more useful to add a perfect prediction line. So write, the dashed diagonal line represents the perfect predictions. A point exactly on the line means actual score equal to predicted score. Points above the line indicate over prediction. The model predicted a score higher than the actual score. Points below the line indicate under prediction. The farther a point is from the line, the larger the error is. This plot helps us to see whether the model performs consistently across low, medium, and high scores. However, a visually attractive plot does not automatically prove that the model is reliable. We still need numerical metrics and careful validation. Linear regression allows us to inspect the learned coefficients. Read a table. The coefficient tells us how the model's prediction changes when one feature increases by 1 unit, while the other model inputs remain fixed. For example, suppose the coefficient for study hours is 2.1. The model is saying that one additional study hour is associated with an increase of approximately 2.1 points in its predicted final score, assuming the other feature values remain fixed. But this is not proof that forcing every student to study one additional hour will cause an exact 2.1 point increase. Why not? Because features can be related to one another. Students who study more may also have higher attendance, stronger previous score, better support systems, or greater motivation. There may also be important variables missing from the dataset. Therefore, coefficient describe the model's learned relationship. They are not automatically causal effects. Let us also inspect the intercept. The intercept is the model's starting value when all features are 0. In some datasets, this value may not have a useful real-world interpretation. For example, a student with 0 attendance, 0 previous score, 0 sleep, and 0 participation may not represent a realistic case. So, not every mathematical component needs a strong practical interpretation. Now, let us predict the score for a hypothetical new student. Before continuing, check that the column names and order match the features used during training. Now predict the score. This is an example of inference. Training happened when we called model.fit. Inference happens when we use the training model to predict an unseen case. The result is an estimate, not a guarantee. The student's actual result could differ because human performance depends on many factors that are not fully captured by the model. We should also be careful when providing values far outside of training range. If the model was trained on students studying between 1 and 8 hours, predicting for someone studying 20 hours would be an extrapolation. The model may produce a number, but that number may not be trustworthy. Now it is time for today's challenge. Your task is remove one feature, retrain the model, and compare the new MAE with the original MAE. Then explain why the result may have changed. You may remove previous score, study hours, attendance, or another feature. I will show you only the first useful step. Suppose we remove previous score. Then reduced features will become this. It will become study hours, attendance, sleep hours, and participation. And we will then do x reduced equal to df reduced features. Now you need to split the reduced feature table, create a new linear regression model, train it, generate predictions, calculate the new MAE, and compare it with the original MAE. Pause the lesson and try it yourself. Now let us discuss one possible solution. We are using the same random state. This helps us compare the models using the same testing rules. Now train the reduced model. Actually, we need to see DF. So let us remove the participation only. So we can remove the participation and keep sleep hours. Now generate the predictions. Calculate the new MAE. Now compare the results. If this new MAE is higher, removing the feature reduce the model's predictive ability on this test set. This may mean that the removed feature contained useful information. For example, previous performance may be strongly related to future performance. If the new MAE becomes lower, it does not automatically mean that the removed feature is useless. Possible reasons include the dataset is small, the test split contains random variations, the feature overlap heavily with the feature overlaps heavily with the other features, the feature contains noise, or the original model may have fitted unnecessary patterns. A single train test split is useful for learning, but it is not enough for a final scientific conclusion. Later, we can use techniques such as cross-validation to obtain a more stable performance estimate. Now, let's discuss some common mistakes. First mistake is treating coefficient as proof. The first common mistake is interpreting model coefficient as causal effects. Suppose study R's have positive coefficient. We can say in this fitted model, higher study R's are associated with a higher predicted score when the other model inputs are held fixed. We should not immediately say one extra hour of study causes the score to rise by exactly this amount. To make a strong causal claim, we need appropriate study design, better control of confounding factors, and often additional analysis. Second mistake is evaluating on training data. Another mistake is calculating performance only on the training set. The model has already seen those examples. Training performance may look unrealistically strong. We should evaluate the model using unseen testing data. Third mistake is ignoring the baseline. A model may produce an MAE that appears reasonable, but without a baseline, we do not know whether it is actually useful. If simply predicting the average scores produces almost the same error, the machine learning model may not be adding much value. Fourth mistake is looking only at R squared. A high R squared does not guarantee that every individual prediction is accurate. It also does not prove causation. We should examine MAE, RMSE, visual patterns, large errors, and the real world context. Fifth mistake is using unrealistic new inputs. The model should generally be used on cases that resemble the training data. Predictions far outside the observed feature ranges may be unreliable. Sixth mistake is assuming one split gives the final answer. Performance can change depending on whether the rows enter the training and testing sets. Performance can change depending on which rows enter the training and testing sets. A single split is a useful starting point. For stronger evaluation, we would repeat the process or use cross-validation. For today's learner evidence, write one sentence that explains the output without technical jargon. For example, the linear regression model predicted students' final scores more accurately than simply assigning every student the average score, although its predictions were still off by several points on average. Adjust the sentence according to your actual results. You may also write removing previous scores or removing participants.